Before we talk about gas lift, let's start with the bigger picture. The ultimate goal of every production engineer is simple: get hydrocarbons from the reservoir to the surface safely and economically. When a field is young, reservoir pressure is often high enough for the well to flow naturally. However, as production continues, reservoir energy gradually declines. The well may still contain significant reserves, but it no longer has enough energy to lift fluids to the surface efficiently. This is where artificial lift becomes essential. Artificial lift methods provide additional energy to help move fluids from the reservoir to the surface. Different technologies achieve this in different ways. Some use mechanical pumps, while others use injected gas. In this chapter, we are focusing on gas lift, one of the most versatile and widely used artificial lift methods in the petroleum industry. By understanding gas lift, you'll learn not only how to increase production from declining wells, but also how production engineers optimize well performance throughout the life of a field. Now that we understand why artificial lift is needed, let's look at what you should be able to achieve by the end of this chapter. This slide outlines the 3 key skills you'll develop in this chapter. First, you should be able to explain the working principle of gas lift. That means understanding exactly how gas injection helps a well produce more efficiently. If you understand the physics behind gas lift, everything else becomes much easier. Second, you should be able to graphically design a gas lift system. Production engineers often use pressure depth plots and gradient diagrams to determine where gas should be injected and how the system will behave. These graphical methods remain an important engineering tool because they help us visualize what is happening inside the wellbore. Third, you should be able to calculate the amount of gas and pressure required for injection. This is the practical engineering part. A gas lift system is only effective if we inject the right amount of gas at the right pressure. Too little gas gives poor lifting performance, while too much gas wastes energy and can even reduce production. By the end of this chapter, you should not only know what gas lift is, but also be able to design and evaluate a gas lift system from an engineering perspective. Now let's start with the fundamentals and look at how gas lift actually works inside the well. Let's start with a simple question. If the reservoir contains oil, why doesn't it keep flowing forever? The answer lies in reservoir energy. During the early life of a well, the reservoir pressure is high enough to push fluids naturally to the surface. As production continues, however, reservoir pressure gradually declines. Notice the graph on the left. The reservoir pressure decreases over time, and as a consequence, the flowing bottom hole pressure also changes. Eventually, the well reaches an economic limit when natural flow is no longer sufficient to deliver the desired production rate. When that happens, several problems appear. Production rates decline, operating costs increase, revenue decreases, and in some cases the well may become uneconomic even though significant oil remains in the reservoir. This is where artificial lift comes in. Artificial lift provides additional energy to the production system. Instead of relying entirely on reservoir pressure, we assist the lifting process by reducing the flowing bottom hole pressure and improving production performance. The important point is this: artificial lift doesn't create more oil in the reservoir. It helps us recover more of the oil that is already there by overcoming the lifting challenge. That's why artificial lift plays such a critical role in extending well life, maintaining production, and improving overall field economics. So whenever reservoir energy is no longer enough to lift fluids economically, artificial lift becomes the bridge between remaining reserves and profitable production. One of the biggest mistakes in production engineering is assuming there is a single best artificial lift method. In reality, the best method depends entirely on the conditions of the well and reservoir. This slide summarizes the 4 major groups of factors we evaluate. Let's start with the well factors. The most important parameters are the productivity index, or PI, and the expected production rate. High-rate wells often favor systems such as continuous gas lift, ESPs, or hydraulic pumps. On the other hand, shallow wells producing smaller volumes may be better suited to sucker rod pumps. For deep directional wells, hydraulic systems are often considered because of their operational flexibility. Next are the reservoir factors. We need to understand the reservoir drive mechanism and the overall reservoir condition. For example, if a water drive reservoir has access to high-pressure gas, gas lift can become a very attractive and cost-effective option. The third group is the fluid factors. Fluid properties often drive the final decision. High GOR fluids create challenges for many pumping systems because gas interference reduces pump efficiency. Gas lift handles free gas extremely well, which is one of its major advantages. We also need to consider issues such as viscosity, fluid density, paraffin deposition, and fluid composition. For example, highly viscous oils may favor sucker rod pumps, while paraffin-prone systems can create problems for certain hydraulic pumps. Finally, we consider environmental factors. Today, environmental performance and operational footprint are increasingly important. We generally prefer systems that reduce emissions, minimize spills, and require fewer interventions. Gas lift and hydraulic systems are often attractive from this perspective. So, whenever you're selecting an artificial lift system, think of it as balancing 4 questions. What can the well deliver? What does the reservoir look like? What fluid are we producing? What are the environmental and operational constraints? Only after answering these questions can we confidently choose the most appropriate lift method. We've discussed how engineers select the most suitable artificial lift method. Once gas lift has been chosen, the next question becomes, how do we design the system? This slide gives us the overall roadmap, from understanding the well's pressure profile all the way to optimizing production. This slide introduces the basic reason artificial lift becomes necessary during a well's life. When a well is first put on production, reservoir pressure is usually high enough to push fluids naturally to the surface. Production rates are often strong because the reservoir still contains significant energy. However, reservoirs don't maintain that energy forever. As fluids are produced, reservoir pressure gradually declines. At the same time, the hydrostatic weight of the fluid column inside the well remains a major challenge. Eventually, the reservoir may still contain a large amount of recoverable oil, but it simply can't provide enough pressure to lift that oil efficiently to the surface. That's where artificial lift comes in. Instead of relying entirely on reservoir energy, we provide additional assistance. In the case of gas lift, we inject gas to reduce the density of the fluid column. By making the fluid column lighter, we reduce the pressure required to lift fluids and allow production to continue at an economical rate. A key point to remember is this: artificial lift does not create more oil in the reservoir. It helps us recover more of the oil that is already there. Now that we've established why artificial lift is needed, let's look more closely at the gas lift system itself and understand how the equipment is arranged in the well. Before we decide to use gas lift, we need to ask an important engineering question. Why gas lift instead of another artificial lift method? This table compares several common artificial lift systems, including rod pumps, PCPs, ESPs, hydraulic pumps, plunger lift, and gas lift. What stands out immediately is that there is no perfect artificial lift method. Every system has strengths and limitations. Let's focus on gas lift. One major advantage is its ability to handle very high production rates, up to around 50,000 barrels of fluid per day. That's significantly higher than many other lift methods. Gas lift is also excellent at handling free gas. In fact, while gas often causes problems for pumps, gas lift actually uses gas as part of the lifting process. That's why it's commonly selected for wells with high GOR. Another advantage is its corrosion tolerance and offshore suitability. Since there are very few moving parts downhole, maintenance is often simpler and intervention can frequently be performed using wireline instead of pulling the tubing. Now, gas lift isn't perfect. If you look at the efficiency row, you'll notice that gas lift typically has lower overall efficiency than some pump systems. It also requires a reliable supply of high-pressure injection gas and compression facilities. So the key takeaway is this: engineers don't choose the best artificial lift method in general. They choose the best method for a specific well. For high-rate wells, offshore operations, deviated wells, or wells producing significant gas, gas lift is often one of the strongest candidates. Now that we've compared gas lift with other artificial lift methods, let's take a closer look at the main advantages and limitations of gas lift itself. This slide shows the fundamental principle behind gas lift, and once you understand this, the rest of gas lift design becomes much easier. The objective of gas lift is not to push oil directly to the surface. The real objective is to reduce the density of the fluid column inside the tubing. Let's follow the process from left to right. First, high-pressure gas from a surface compressor is injected down the annulus. The gas then enters the tubing through a gas lift valve. Once inside the tubing, the gas mixes with the produced liquids. As the gas expands, it forms bubbles throughout the fluid column. Now here's the key point. A gas-liquid mixture is much lighter than liquid alone. Because the fluid column becomes lighter, the hydrostatic pressure acting against the reservoir decreases. The reservoir no longer has to work as hard to move fluids into the wellbore and up to the surface. In the center diagram, you can see this effect represented by the VLP curve shifting downward. The IPR remains unchanged because the reservoir hasn't changed. What changes is the lifting performance of the well. The result is a new operating point at a higher production rate. So whenever someone asks, how does gas lift increase production? The short answer is, gas lift lowers the hydrostatic head, reduces flowing bottom hole pressure, improves inflow from the reservoir, and increases production. That's the entire physics of gas lift in one sentence. Now that we understand the principle, let's look at the two main ways gas lift systems are operated: continuous gas lift and intermittent gas lift. This slide introduces the two main operating modes of gas lift: continuous gas lift and intermittent gas lift. Let's start with continuous gas lift, shown on the left. In continuous gas lift, high-pressure gas is injected continuously into the tubing. The gas mixes with the produced fluids, reducing the fluid density and allowing the reservoir to deliver fluid steadily to the surface. This method works best when the well has a high productivity index, typically greater than about 0.5 stb a day psi, and still has reasonable reservoir pressure. Because the well can continuously supply fluid to the tubing, continuous gas lift can achieve relatively high and stable production rates. Now let's compare that with intermittent gas lift, shown on the right. Intermittent gas lift operates in cycles rather than continuously. Gas is injected periodically to push accumulated liquid slugs from the bottom of the well to the surface. After one slug is lifted, the well is allowed to refill before the next cycle begins. This method is generally used when the well cannot sustain continuous flow. That may be due to low reservoir pressure, low productivity, or insufficient fluid inflow. In practice, it is commonly applied to wells with a PI less than about 0.5 stb a day of psi. The trade-off is that intermittent gas lift typically produces lower overall rates because production occurs in batches rather than continuously. A simple way to remember the difference is, continuous gas lift equals steady flow, higher rate wells. Intermittent gas lift equals cyclic flow, lower rate wells. The choice between the two depends primarily on the well's ability to continuously supply fluid to the tubing. Now that we've seen the two operating modes, let's examine how engineers optimize gas injection to achieve maximum production performance. One of the biggest misconceptions in gas lift is that injecting more gas will always produce more oil. In reality, that's not how the system behaves. When gas injection starts, production increases because the injected gas reduces the density of the fluid column. The well becomes easier to lift, flowing bottom hole pressure decreases, and reservoir inflow improves. Initially, every additional unit of gas gives a noticeable production gain. However, this improvement does not continue forever. As gas injection keeps increasing, the tubing begins to carry larger gas volumes. Eventually, friction losses inside the tubing start increasing significantly. At that point, the benefit gained from reducing hydrostatic pressure becomes smaller than the penalty created by friction. This creates an optimum point on the curve. On the graph, you'll notice that production increases from QO to QG, reaches a maximum, and then begins to decline when excessive gas is injected. This optimum point is what production engineers are trying to find during gas lift optimization. The objective is not maximum gas injection. The objective is maximum oil production with minimum gas consumption. In real field operations, this optimization is extremely important because injection gas is valuable. Every additional unit of gas requires compression power, operating cost, and facility capacity. A well-designed gas lift system therefore operates near the optimum gas injection rate, where production is maximized and gas utilization is most efficient. We've just seen that optimizing gas injection is only part of the challenge. Before we can optimize anything, we first need to select the right artificial lift method for the well. That decision depends on several technical, reservoir, fluid, and environmental factors, which we'll look at next. This slide provides a high-level overview of the intermittent gas lift design process. Think of it as the workflow a production engineer follows when designing a gas lift system. The first step is to build the pressure profile of the well. Before making any design decisions, we need to understand how pressure changes with depth. This allows us to identify the reservoir pressure, flowing bottom hole pressure, and pressure gradients throughout the well. Next, we select the lowest operating pressure. Our goal is to find the deepest practical valve location because deeper gas injection generally improves lifting efficiency. The operating valve depth is determined by the pressure relationship between the tubing and casing. Once the operating point is identified, we calculate the weighted average flowing bottom hole pressure. This gives us a representative pressure condition for evaluating well performance and designing the operating cycle. The fourth step is to determine the feed-in rate and cycle time. Unlike continuous gas lift, intermittent gas lift works in cycles. Fluid accumulates in the tubing, gas is injected, the liquid slug is lifted to the surface, and then the process repeats. Therefore, selecting the correct feed-in time and cycle frequency is critical for maximizing production. Finally, we optimize the injection strategy. This is where engineering judgment becomes important. We evaluate different cycle frequencies and injection volumes to identify the operating condition that delivers the highest daily liquid production while remaining within compressor and gas supply limitations. Although the calculations can become detailed, the overall objective is quite simple. Find the operating conditions that lift the maximum amount of fluid using the minimum amount of gas. That is the essence of good gas lift design. Now that we've seen the design workflow, let's step back and look at the actual equipment that makes gas lift possible. A gas lift system isn't just a valve downhole. It's a complete system that starts at the surface and extends all the way to the reservoir. This slide shows the major components of a gas lift system and how they work together as a single production system. Let's start on the surface side. Everything begins with the gas source, which is usually a compressor. The compressor provides the high-pressure gas required for injection. The gas then passes through aftercoolers and filters. These components remove heat, moisture, and contaminants. Clean, dry gas is important because water, solids, and debris can damage valves and reduce system reliability. Next, the gas flows through control valves and instrumentation. These devices allow engineers to monitor pressure, temperature, and flow rate while controlling the amount of gas being injected into the well. The gas then enters the wellhead and travels down the annulus between the tubing and casing. Now let's look at the downhole equipment. The most important component is the gas lift valve. This valve allows gas to enter the tubing at a predetermined depth when the required pressure conditions are met. The valve is installed inside a gas lift mandrel, which provides the connection point between the annulus and the tubing. The tubing serves as the production conduit, carrying the gas-liquid mixture to the surface. Further downhole, you'll often find a packer. The packer seals the annulus and prevents gas from bypassing the intended injection path. This ensures that the injected gas reaches the correct valve and performs useful work. Some installations also include safety valves that provide emergency shut-in capability if abnormal conditions occur. The key point is that gas lift is not a single piece of equipment. It is an integrated system where compressors, control equipment, valves, mandrels, tubing, and packers must all work together to produce the well efficiently and safely. We've looked at the individual surface and downhole components. The next step is understanding how these components are arranged inside a real continuous gas lift well and why each component is placed where it is. This slide shows a typical continuous gas lift installation and how all the components work together inside the well. Let's start at the surface. High-pressure gas from the compressor enters the wellhead and is directed into the casing annulus, which is the space between the casing and tubing. The gas then travels downward through the annulus until it reaches a gas lift valve. These valves are installed at selected depths and provide controlled entry points for gas into the tubing. Notice that this installation contains multiple valves at different depths. During unloading, the upper valves assist first. As the well becomes lighter and tubing pressure decreases, the injection point progressively moves deeper until the operating valve takes over. The operating valve is usually the deepest active valve because deeper injection generally provides better lifting efficiency and greater reduction in hydrostatic pressure. Inside the tubing, the injected gas mixes with the produced fluid. This creates a lighter gas-liquid mixture, reducing the overall fluid density and allowing the reservoir to lift fluids more easily to the surface. Another important component is the packer near the bottom of the tubing. The packer seals the annulus and prevents gas from bypassing the intended flow path. Without the packer, injected gas could simply move around the tubing instead of entering through the gas lift valves. From a design perspective, engineers are trying to achieve four things: Place the operating valve as deep as practical. Ensure sufficient pressure differential for gas injection. Maintain stable production. Maximize production while minimizing gas consumption. So this slide isn't just showing equipment placement. It's showing a carefully engineered pressure management system designed to help the reservoir produce efficiently. We've now seen where gas lift valves are located in the completion. Next, we'll focus on the gas lift valve itself, because understanding how the valve operates is essential for understanding the entire gas lift system. At its core, a gas lift valve is a downhole pressure regulator. Its job is actually quite simple. Allow injection gas to enter the tubing when the correct pressure conditions exist and restrict or stop gas flow when those conditions change. The valve is installed inside a gas lift mandrel, which is attached to the tubing string. This arrangement allows gas to travel from the annulus into the tubing at selected depths. Now, the requirements of the valve depend on the type of gas lift operation. For continuous gas lift, the valve must provide controlled and stable gas injection. It needs to continuously deliver gas into the tubing, maintain stable operating conditions, and regulate the injection rate. Depending on the design, the valve can respond to casing pressure, tubing pressure, or a combination of both. For intermittent gas lift, the valve behaves differently. Instead of providing continuous flow, it must open quickly when the required pressure is reached, remain fully open during the lifting cycle, and then close once the cycle is completed. This rapid open and close action is essential for efficiently lifting liquid slugs to the surface. Let's also look at the major valve components. The body provides the structural housing. The loading element, which may be a spring, compressed gas charge, or a combination of both, supplies the force that helps control valve movement. The bellows, piston, or diaphragm acts as the sensing element, responding to pressure changes. The stem transfers that movement to the valve mechanism. And finally, the orifice or port meters the gas flow entering the tubing. So although the valve looks like a small component, it performs several critical functions. As the name suggests, a combination valve combines features of both pressure-operated and fluid-operated valves. The upper section works like a conventional pressure-operated valve, responding to casing pressure. The lower section contains a fluid pilot mechanism, which responds to the fluid pressure inside the tubing. Why combine both? Because relying on only one pressure source doesn't always provide the most reliable control. By considering both casing and tubing conditions, the valve can make better decisions about when to open and close. Think of it as using two sensors instead of one. The valve gets information from both sides of the system before responding. This gives engineers greater flexibility in complex wells where operating conditions can change significantly over time. Although the design is more sophisticated, the objective remains the same. Inject gas at the right depth, at the right time, and in the right amount. So the combination valve is essentially a hybrid design that combines the strengths of pressure-operated and fluid-operated valves into a single system. Now that we've covered the main valve types, let's look at actual gas lift valve assemblies and see what these components look like in real field equipment. Let's take a closer look at the actual hardware used in a gas lift completion. On the left, we have the gas lift mandrel. Think of the mandrel as the housing that holds the gas lift valve inside the tubing string. You'll notice components such as the orienting sleeve, pocket, and swage sections. The most important part is the side pocket, where the gas lift valve is installed. This design allows the valve to be retrieved or replaced by wireline without pulling the entire tubing string, which significantly reduces intervention costs. On the right, we see examples of locks and latches. These are used to securely position the gas lift valve inside the mandrel pocket and prevent movement during operation. The cross-sectional views show how the valve sits inside the mandrel, creating a controlled flow path from the casing annulus into the tubing. The key takeaway is that the mandrel provides the structure, the latch secures the valve, and the valve controls gas injection. Together, they form the foundation of a reliable gas lift system. Now that we've seen the equipment itself, the next question is how these components are arranged in different well completions. That's where gas lift installation types become important. Before selecting a gas lift installation, engineers need to evaluate two things: the well requirements and the installation type. On the left, we have the factors that influence our decision. First, we look at the well condition and completion design. Not every completion can accommodate the same gas lift configuration. We also need to consider potential production issues such as sand production, water coning, or gas coning. because these can affect long-term performance. Another critical consideration is the future behavior of the well. Reservoir pressure declines over time, and productivity index may decrease, so the installation should remain effective as the well matures. Once these factors are understood, we choose the most suitable installation type. The 4 common configurations are open installation, semi-closed installation, closed installation, chamber installation. Each configuration provides a different level of control, flexibility, and suitability for specific operating conditions. So the key message is simple. Good gas lift design isn't just about choosing valves. It's about selecting an installation that matches both the current well conditions and the future performance of the well. Let's start with the simplest configuration of all, the open installation, and see where it works well and where it creates operational challenges. Focus on the 2 curves. The red curve represents casing pressure. As gas is injected, casing pressure builds up until a valve opens and gas enters the tubing. The green curve represents tubing pressure. Notice the repeated pressure spikes. Each spike corresponds to a stage of the unloading process, where gas enters the tubing and displaces fluid. As unloading progresses, the active injection point moves deeper, and the casing pressure gradually stabilizes. Eventually, both pressures level out. This indicates that unloading is complete and the well has reached its normal operating condition, with gas being injected through the operating valve. So this chart is essentially the pressure signature of a successful unloading operation. Once the well reaches stable operation, the next challenge is designing the gas lift system itself, starting with the injection point, gas requirement, and injection pressure. Every gas lift design starts with 3 key questions. Where should we inject the gas? How much gas do we need? And what injection pressure is required? To answer these questions, engineers collect critical well data such as well depth, production target, tubing size, water cut, gas-liquid ratio, reservoir pressure, productivity index, and available injection pressure. Using this information, we construct pressure gradient relationships for the well. These pressure profiles help us identify the optimum injection point and estimate the gas volume needed to achieve the desired production rate. The quality of the design depends directly on the quality of the input data. Good data leads to an efficient gas lift system. Poor data can result in excessive gas consumption or poor production performance. So before drawing any gradients or selecting any valves, we first build a complete picture of the well. Let's now visualize a typical continuous gas lift well and identify the key pressures and flow paths used in the design process. This figure brings together the main elements of a continuous gas lift system. Gas is injected from the surface and travels down the annulus. During startup, the gas enters through the unloading valves, helping remove the heavy fluid column. As unloading progresses, the injection point moves deeper until gas reaches the operating valve, which becomes the permanent injection point during normal production. You can also see the packer, which isolates the annulus and forces gas to enter the tubing through the valves rather than bypassing them. 2 important gradients are shown. GU, pressure gradient above the injection point. GR, pressure gradient below the injection point. You'll also notice the point of balance, which is a key design concept used later to determine the optimum injection depth. This sketch is essentially the roadmap for the design procedure we'll follow in the next few slides. We've identified the operating valve. Now let's see the pressure logic that determines where gas can actually be injected. This is one of the most important diagrams in gas lift design. The curved line on the left, GFA, represents the tubing pressure gradient above the injection point. The line on the right, GFB, represents the tubing pressure gradient below the injection point. The vertical line represents the casing pressure. Notice the point of balance. This is where tubing and casing pressures become equal. At this point, gas can no longer naturally enter the tubing. Therefore, the actual gas injection point must be located slightly above the point of balance. We maintain a pressure differential, PV, to ensure gas flows from the annulus into the tubing. The deeper we can place the operating valve while still maintaining this pressure differential, the more efficiently we reduce the hydrostatic head and lift the well. So this diagram is really answering one question. Now let's put this pressure relationship into equation form and see how engineers calculate the pressures at different depths. This equation simply accounts for the pressure changes from surface to bottom hole. Starting from the tubing pressure, We add the pressure losses above the injection point and below the injection point to obtain the flowing bottom hole pressure, PWF. The important takeaway isn't the equation itself. It's understanding that the injection depth, pressure gradients, and tubing pressure all influence the final bottom hole pressure, which ultimately controls well performance. Before starting detailed calculations, engineers use these guidelines as quick checks. For continuous gas lift, a typical pressure requirement is about 100 psi per 1,000 feet of lift, usually between 300 and 800 psi. Gas requirements are often estimated at 150 to 250 SCF per barrel per 1,000 feet of lift. We also estimate the maximum achievable injection depth from the pressure difference between casing and tubing. Finally, the gas column itself contributes pressure, which must be included when determining casing pressure at depth. These aren't final design calculations. They're screening tools that help us quickly assess whether a gas lift design is realistic. Tubing size has a major impact on the production rate that a gas lift system can handle. As tubing diameter increases, the maximum achievable production rate also increases. For example, a 1-inch tubing may handle only a few hundred barrels per day, while a 4-inch tubing can accommodate several thousand barrels per day. The table provides quick design guidelines for selecting an appropriate tubing size based on the expected production range. The key message is simple. Undersized tubing restricts production, while oversized tubing can reduce flow efficiency. The tubing size should match the production target. Temperature increases as we go deeper into the well, and this affects fluid properties, gas behavior, and pressure calculations. This simple equation estimates the temperature at any depth using the surface temperature and the geothermal gradient. In gas lift design, accurate temperature estimates are important because temperature directly affects gas density and pressure calculations. We start by plotting the reservoir pressure, PS, at reservoir depth. Using the well's PI, we calculate the pressure drawdown and determine PWF, the flowing bottom hole pressure. Next, we draw the static pressure gradient, GS, upward from PS until it reaches the depth axis. This gives us point A, known as the static fluid level. In simple terms, it's the level where fluid would naturally stand in the well if the system reached pressure equilibrium. This static fluid level is one of the key reference points used later to determine the optimum gas injection depth. This chart is used to determine the static pressure gradient, GS, based on the water cut or saltwater percentage. The higher the water content, the heavier the fluid column and the larger the pressure gradient. In practice, we enter the chart using the well's water cut, read the corresponding gradient, and then use that value to determine the static fluid level and build the pressure depth plot. This is one of the first inputs required when locating the gas injection point. Next, we establish the flowing pressure gradient below the injection point, GFB starting from PWF. If detailed flow data isn't available, a common assumption is that GFB is approximately equal to the static gradient, GS. Where this gradient intersects the depth axis gives point A, known as the working fluid level. Unlike the static fluid level, this represents the fluid level during production. Next, we plot two important surface pressures. Kickoff pressure minus 50 psi. Operating casing pressure, PSO. These pressures will later help us determine the balance point and ultimately the gas injection depth. Next, we project the operating casing pressure, PSO, downward while accounting for the weight of the gas column. This gives us the casing pressure gradient inside the well. Where this line intersects the flowing pressure gradient below the injection point, GFB, we obtain point B, known as the point of balance. At this point, tubing pressure and casing pressure are equal. This is critical because it helps us determine how deep we can inject gas and serves as the reference for locating the operating valve. Instead of calculating gas column pressure manually, engineers often use this chart. Starting from the surface casing pressure, we move across the appropriate gas gravity line and read the pressure at depth. The result is the casing pressure at valve depth, which is required to draw the casing pressure gradient and locate the point of balance. Think of this chart as a quick shortcut for converting surface pressure into downhole pressure. Here's a practical example of how the gas column chart is used. Starting with a surface operating pressure of 600 psi, we follow the gas gravity line to the required depth. The chart shows that 600 psi at surface corresponds to approximately 704 psi at 8,000 feet. This downhole casing pressure is then used to construct the casing pressure gradient and determine the balance point and injection depth. so the chart helps us quickly convert surface pressure into operating pressure at depth. Now we determine the actual injection point. Starting from the point of balance, B, we move down by 100 psi to locate point C, which becomes the gas injection point. Next, we plot the flowing wellhead pressure, PWH. Finally, we connect PWH to the injection point using the appropriate pressure distribution curve. This gives us GFA, the flowing pressure gradient above the injection point. The selected curve must reflect the total GLR, which includes both formation gas and injected gas. At this stage, the injection point location is finalized. This slide is where everything comes together. Let's imagine we are designing a gas lift system for a real well. We start with the reservoir pressure, PS, and the flowing bottom hole pressure, PWF. From these values, we establish the pressure gradients inside the well. The line GS represents the static fluid column, while GFB represents the pressure profile during production. Next, we draw the operating casing pressure gradient. Where this line intersects GFB, we get point B, the point of balance. At point B, tubing pressure and casing pressure are equal. Since gas only flows from high pressure to low pressure, we cannot inject gas at this exact location. That's why we move 100 psi to the left to create a pressure differential. This gives us point C, the actual injection point. In practical terms, C is where we place the operating gas lift valve. The deeper this point is, the more fluid column we can lighten, which generally means better lifting performance and higher production. Also notice the two fluid levels. A is the static fluid level before production. E is the working fluid level during production. As engineers, our goal is to use all these pressure relationships to find the deepest injection point that still allows gas to enter the tubing efficiently. So if someone asks, what is the purpose of this entire procedure? The answer is simple. We are finding the optimum depth to install the operating gas lift valve. Before we move into the worked examples, I'd like to introduce the companion dashboard developed for this chapter. The dashboard allows you to change inputs such as reservoir pressure, PI, production rate, gas gravity, tubing size, and injection pressure, and immediately see how the injection point changes. Instead of manually redrawing every gradient, you can visualize the complete design process in real time. As we work through the next few examples, you'll notice the dashboard follows exactly the same steps we've just learned: calculating PWF, locating point B, determining point C, estimating gas requirements, and eventually designing valve spacing. Use it as a learning tool first. The goal is not to replace the graphical method, but to help you understand how changing one parameter affects the entire gas lift design. Now let's apply the procedure using a real field example. All the required data is provided, including reservoir pressure, PI, tubing size, fluid properties, and operating pressures. Using the steps we've just covered, your task is to determine the gas injection depth and estimate the gas injection requirement for continuous gas lift. Let's work through it systematically and see where the operating valve should be placed. For this example, we first calculate the flowing bottom hole pressure, PWF, using the productivity index relationship. Next, using the saltwater gradient chart in slide 37, we determine the static fluid level, point A, and working fluid level, point E. We then calculate the casing pressures for PKO 50 and PSO at depth using the weight of gas column chart in slide 40. These values will be used to construct the pressure depth plot and locate the balance point and injection point. I'll leave the detailed calculations for you to review, and we'll focus on the engineering interpretation. After completing the pressure depth plot, we locate the point of balance, B, at 980 psi. Subtracting 100 psi gives point C, the injection point. From the graph, the operating valve depth is approximately 5,600 feet. Using the gas lift design guideline, the required injection gas ranges between 672 and 1,120 MSCF a day. The important result here is not the calculation itself. It's identifying the injection depth and estimating the gas requirement. This is the completed pressure depth plot for example 4.1. Notice how all the gradients come together to locate the point of balance, B, and the injection point, C. Rather than focusing on every line, focus on the outcome. From the plot, we determine an injection depth of approximately 5,600 feet and use that value to estimate the gas injection requirement. This is exactly how graphical gas lift design is performed in practice. To determine the injection point accurately, we need two pressure traverses. The traverse above the injection point starts from the flowing wellhead pressure, PWH. The traverse below the injection point starts from the flowing bottom hull pressure, PWF. These traverses can either be traced directly from pressure distribution charts or plotted using data extracted from those charts. Once both traverses are established, we can identify where the pressure profiles meet the gas lift operating conditions and complete the design. To establish GFA, we first select the correct pressure distribution curve based on tubing size, production rate, temperature, and GLR. Next, we plot the flowing wellhead pressure, PWH. Then we overlay the graph on the selected pressure distribution chart and shift it until PWH falls on the appropriate GLR curve. Once aligned, we can trace the tubing pressure profile above the injection point. The goal is simply to construct GFA, the pressure traverse above the operating valve. The procedure for GFB is almost identical to GFA. Instead of starting from PWH, we start from the flowing bottom hull pressure, PWF. We align PWF with the appropriate formation GLR curve, then trace the pressure profile upward toward the injection point. At the end, we have the tubing pressure traverse below the injection point, completing the pressure profile needed for gas lift design. Once we've selected the correct GLR curve, we determine the chart depth correction, CDC. We then add this correction to the actual depths to obtain equivalent chart depths. Using those equivalent depths, we read the corresponding tubing pressures from the pressure distribution chart. These pressure depth points are then used to construct GFA, the tubing pressure traverse above the injection point. Once the pressures are obtained, we simply organize the results in a table. For each actual depth, we determine the equivalent chart depth and the corresponding tubing pressure. These pressure depth points are then plotted to create GFA, the flowing tubing pressure traverse above the injection point. The table is just a structured way of converting chart readings into a pressure profile. This figure shows the graphical method for determining GFA. Starting from PWH, we apply the chart depth correction, move to the appropriate GLR curve, and read the tubing pressures at different depths. Those pressure depth points are then plotted to establish the flowing tubing pressure traverse above the injection point. This is a typical pressure distribution chart used throughout gas lift design. Each curve represents a different GLR condition. By selecting the correct curve and applying the chart depth correction, we can estimate tubing pressures at various depths. In practice, this chart is the source of the pressure data used to develop GFA and GFB. This figure shows how we determine GFB, the flowing pressure traverse below the injection point. Starting from the known PWF of 2,600 psi at 8,000 feet, we move upward along the formation GLR curve and read the tubing pressures at successively shallower depths. These pressure depth points are then used to construct GFB, which represents the tubing pressure profile below the injection point. For GFB, we start from the known PWF and locate it on the appropriate formation GLR curve. This gives us the chart depth correction. We then calculate equivalent chart depths at shallower intervals and read the corresponding tubing pressures from the chart. These values will later be used to construct the flowing pressure traverse below the injection point. After obtaining the equivalent chart depths, we read the corresponding tubing pressures from the pressure distribution chart. We then tabulate the pressure depth data and plot pressure versus actual depth. The resulting curve is GFB, which represents the flowing tubing pressure traverse below the injection point. This figure shows the graphical construction of GFB. Starting from the known PWF, we apply the chart depth correction, move along the formation GLR curve, and read the tubing pressures at shallower depths. These points are then connected to generate the flowing tubing pressure traverse below the injection point. Here's another design example. This time, you're given the production rate, tubing size, pressures, temperatures, GOR, and injection gas conditions. Using the pressure traverse method we just learned, determine two things: the injection point depth, the required gas injection rate. Focus on the procedure rather than the arithmetic. If the method is correct, the answer will follow. The first step is to calculate the formation GLR, which in this example is 50 SCF BBL. Using that GLR, we select the appropriate pressure distribution chart and construct GFB, the pressure traverse below the injection point. The table simply summarizes the pressure values obtained at different depths. Focus on the method, determine the GLR, select the correct chart, then build the pressure traverse. Next, we draw the operating casing pressure gradient. From the gas column chart, a surface pressure of 600 psi corresponds to about 704 psi at 8,000 feet. Using this, we establish the casing pressure profile. We then locate the point where the casing and tubing pressures satisfy the required 30 psi differential across the valve. From the graph, the operating valve depth is approximately 3,480 feet, with a tubing pressure of about 615 psi. Once the injection point is known, we can estimate the gas requirement. Using the pressure distribution chart, we determine the total producing GLR, which is approximately 370 SCF BBL. Subtracting the formation GLR of 50 SCF BBL gives an injection GLR of 320 SCF BBL. For a production rate of 750 BBL a day, the required gas injection rate is approximately 240,000 SCF or day. This slide shows an alternative way to obtain the gas requirement. Once the injection point is known, we plot 615 psi at the equivalent depth of 3,820 feet on the pressure distribution chart. From the chart, we estimate a total producing GLR of about 370 SCF BBL by interpolation. The result is the same as before, which gives us confidence in our design. This is the same pressure distribution chart used in the previous calculations. Once you know the operating conditions, you use the chart to estimate tubing pressures and determine the corresponding GLR. For the exam, focus less on memorizing the chart and more on understanding how to use it. This figure shows how we estimate the total producing GLR. We plot the wellhead pressure and the injection point pressure on the pressure distribution chart, then identify which GLR curve passes through both points. In this example, the value falls between the 300 and 400 SCF BBL curves, giving an estimated total GLR of about 370 SCF BBL. After determining the total producing GLR, we can calculate the required injection gas. The total GLR is 370 SCF per BBL, while the formation contributes 50 SCF per BBL. The difference gives an injection GLR of 320 SCF per BBL. Multiplying by the production rate of 750 BBL per day gives a required gas injection rate of approximately 240,000 SCF per day. This figure summarizes the complete solution. The blue line is the casing pressure gradient, while the green lines represent the tubing pressure traverses above and below the injection point. The operating condition occurs where we maintain the required 30 psi differential between casing and tubing pressure. From the graph, the operating valve is placed at approximately 3,480 feet, with a tubing pressure of 615 psi, and the required gas injection rate is about 240,000 SCF per day. This is the final design result. Everything we've just calculated manually can also be visualized instantly in the companion dashboard. Try changing casing pressure, PI, or water cut and observe how the injection depth and gas requirement change. Once we've determined the operating valve depth, the next task is deciding where to place the unloading valves. Valve spacing depends mainly on the valve type, operating pressure, well flow conditions, and the static fluid level. For balanced valves, spacing is typically based on pressure reductions of about 15 to 25 psi per valve. For unbalanced valves, spacing is based on operating or design casing pressures. The objective is simple. Ensure a smooth unloading process so gas can progressively move deeper until it reaches the operating valve. Before we can design valve spacing, we need the right input data. This includes well geometry, operating pressures, production rate, fluid properties, temperature information, and reservoir performance data such as PI or PWF. Remember, valve spacing is only as good as the data used. If the inputs are wrong, the valve depths will be wrong too. Now we start placing the unloading valves. First, draw the tubing design gradient from the design wellhead pressure to the injection point. Next, draw the kill fluid gradient and extend it until it intersects the casing gradient. That intersection is point D, which represents the first or top unloading valve. In simple terms, this step determines where the unloading sequence begins. Once the first valve is located, the remaining valves are placed using the same graphical method. From point D, move to the tubing design gradient, then draw a line parallel to the kill fluid gradient until it reaches the next casing pressure line. This gives point H, which represents the second unloading valve. The process is then repeated to locate the remaining valves. The process continues until we reach the operating valve. Here, point K gives the depth of the third valve. We keep repeating the same construction steps until the gas injection point is reached. In practice, engineers often place one or two extra valves below the operating valve to provide flexibility for future changes in well performance. This is the complete valve spacing design on a single plot. Let's follow the unloading sequence. The top valve, DV1, is placed at point D. During startup, gas first enters through this valve because it's the shallowest. As the well unloads and tubing pressure decreases, the first valve closes. Gas is then forced deeper to DV2, then DV3, and finally DV4, which is the operating valve near the injection point C. Think of these unloading valves as stepping stones. Their job is not to produce the well permanently. Their job is to progressively move the gas injection point deeper and deeper until the operating valve takes over. Notice how each valve is positioned using the design tubing gradient and casing pressure lines. This ensures that each valve opens and closes in the correct sequence during unloading. If the spacing is poor, two valves may operate simultaneously or a valve may never close properly, resulting in inefficient unloading. A well-designed spacing pattern gives a smooth transition from DV1 to DV2 to DV3 to DV4, allowing the well to reach stable gas lift operation efficiently. The procedure for an unbalanced valve is almost identical to what we've just done for the balanced valve. The main difference is the reference pressure used for setting valve depths. Instead of using the balanced valve pressure lines, we reference either the operating casing pressure gradient, PSO, or the design casing pressure, PSO minus 50 psi. The objective is still the same. Place the unloading valves so they open and close in the correct sequence and gradually transfer gas injection to the operating valve. So the methodology doesn't change much. Only the pressure reference changes. This figure shows the valve spacing design for an unbalanced valve system. The procedure is very similar to the balanced valve case, but notice that the valve depths are referenced to the operating casing pressure, PSO, and the design casing pressure, PKO 50. Starting from PWHD, we use the tubing design gradient and casing pressure lines to determine the unloading valve positions. The objective remains unchanged. Each valve should open, unload a portion of the fluid column, close, and then hand over operation to the next deeper valve until the operating valve is reached. So the physics is the same. Only the pressure reference used for valve placement changes. This figure shows the complete valve spacing design for an unbalanced valve system. We start with the tubing design gradient, which is shifted by 0.25 times PSO from the normal tubing pressure line. The unloading valves are then positioned between the tubing design gradient and the casing pressure gradients, using increments based on PSO and PSO minus 50 psi. Just like the balanced valve design, the objective is to create a smooth unloading sequence. Each valve operates temporarily, allowing gas injection to move deeper until the operating valve takes over. So don't focus on memorizing every line. Focus on the concept. We are creating a controlled pathway that guides the well from startup to normal gas lift operation. This is the final example that brings everything together. You're given the well data, reservoir pressure, operating pressure, fluid properties, and tubing information. Using the procedures we've covered, determine the operating valve depth for a continuous gas lift system using unbalanced valves, the unloading valve spacing required for startup and unloading. Focus on the workflow. Determine the injection point first, then design the unloading valve locations.